theoretician of this country. He is with us, and his long-time friend, Professor Biman Bagchi, will introduce him. Good afternoon. It is a pleasure to have Professor Biman Bagchi among us today. Biman is among the most famous physical chemists ever born in India, and I think he is at present he is among the top 2 physical chemists in the country. Top 2 physical chemists in the country.
Second best physical chemist.
Second best after me. Just I'll tell you a few things about his career. Biman studied in Presidency College. He was 1 year senior to me, and actually he was a classmate of Dev Shankar Rai. After MSc in Calcutta University, he went to Brown University. He did PhD with Julian Gibbs, and then he moved to Chicago University to work with David Oxtoby and Graham Fleming. After that, he had another postdoc with Robert Zwanzig, and he came back to IISc Bangalore in 1984. He was actually offered a job in IACS also, but somehow he thought IISc Bangalore is a better place. And actually, Biman evolved with a very interesting area of physical chemistry. As you know, that historically, statistical mechanics theory was the main branch of physical chemistry, and it started before quantum chemistry, because it was started by people like Maxwell and Boltzmann. But when quantum mechanics came, people got baffled with the glamour of quantum chemistry, and from 1930s to 1940s, Linus Pauling and other people made quantum chemistry so glamorous. Then the most important physical chemistry, theoretical chemistry meeting was named as International Meeting on Quantum Chemistry. But because of people like Onsaga, Levi Huckel and other people, from 1950s people recognized the importance of other field, and that's whatever that conference, Sunnyvale or something, the name of the conference changed to theoretical chemistry. And when Biman started, very little was known as liquids, and experiments was coming in a very big way, and people were applying picosecond spectroscopy and then femtosecond. And at that juncture, Biman with Graham Fleming and Oxtoby wrote some pioneering work on how to explain the rate of chemical processes in liquids. I think the BFO paper, Biman, Fleming and Bagchi, Fleming and Oxtoby, and the other paper on solvation dynamics and isomerization became a citation classic. And in India at that time, the theory was dominated by quantum chemistry, but Biman and Biman's students have largely changed the scenario. And actually Biman's friend Dev Shankar also developed theory in a different, statistical mechanics oriented, but in a different way, different from quantum, traditional quantum chemistry. And Biman has received a large number of awards. Whatever award you can talk of in India, Bhatnagar, Fellowships of All Academy, Third All Academy of Science, all these awards he has got. But I think among all these awards, I think most satisfying was that when Martin Karplus retired from Harvard University, Martin Karplus, as you know, got Nobel Prize in 2013. When he retired, then the Harvard University invited him to become a visiting professor, and he taught the same course which Martin Karplus was teaching at Harvard. And he subsequently visited many other places. He has written more than 400 papers, and we have written some very famous reviews. I think very famous reviews. I think my contribution is more than Biman's contribution in that area. But today he is going to talk on water plus transition. This glassy system is one of his very favorite systems. He has developed a lot of theoretical models as well as simulation. And tomorrow he will talk on this protein folding, which is a very complicated and very interesting subject. And I am very happy that there is a lot of people who have come here, and I hope Biman will teach us through lectures and private discussion. Biman Bagchi, please.
Okay, thank you. Thank you very much. Thank you, Mayan. Thank you, Satyajit and Konkon. I have given here talks now for a very long time. First one I gave was in 1978, when not in this room. So when Konkon was teaching, and I was thinking he might talk, but I was thinking of these past things. Then I think when I gave my first lecture was Konkon was not here. He was with Eisenthal. And so as Konkon said, it's really amazing journey in theoretical chemistry that took place from late 70s all the way till now. And I was lucky to be associated with some experimentalists from the beginning. And I've always worked with experimentalists somewhat better than with theoreticians. Probably because when you work with experimentalists, you can develop new theories. And when you work with a theoretician, you essentially work on a theory, And the danger of writing a footnote is enormous. But if you are lucky to be in contact with an experimentalist who is doing new experiments, then you can be, and you are lucky, again, then you can do something really outstanding and highly influential piece of work, which happened in our case, kind of in a very short span of time, again and again, in the chemical dynamics and solution dynamics and those kind of things. Okay, so as Konkon was saying that the protein and protein foldings are complex, but what I try to tell you today, and that is this thing, in Bengali we say that it's like joler moto soja, but this is probably the most complex and even probably as far as even more complex than anything known on Earth. And what I talk today is that this is a fascinating multi-dimensional structure and dynamics of water, but these undergo some very interesting and very low temperature properties, which now has become the talk of the town almost. As I wrote in my abstract, there are huge number of nature and science and PNAS papers coming out continuously to try to understand properties of water at very low temperature. So there is signatures of that. Okay, if I show that this is something I write in blogs now, and ideally young generation is mostly for students and young faculty, and I invite people to this for science talk in WordPress, and please do read them. Last one that I wrote yesterday I published is on communication, that how to communicate with people. And young faculty, and it's the personal communication, not just the kind of communication that I'm doing now, but it's the communication when you do one-to-one or two-to-one in a short is very important. For example, when you're trying to get a job, then you have to talk with the individual faculty. And if one faculty tells bad things about you, that is the almost end of your getting a chance of getting a job in a department. And I gave several examples from my own recent experiences. So do read them, and I talk some of the ethics and values in science, and it is not boring. It is written very colloquial, informal style, and I think you will like it. Okay. Now coming back to science is what is going on for last 12 or 13 years. I started before 2004, and he was an assistant professor in Nagaraj and Professor Yao Mine. He is retired now from IISc. He was the Director General, and he was a PhD student, very young PhD student then. And when I first met him, which was 1992 or so, he is a senior faculty now with chairman of 3 departments, theoretical chemistry and spectroscopy, computer science, and one more. Very busy man, but we work together a lot, to the extent we Skype sometimes, couple of times a week. Shinji Saito is very famous. He has given 2 Gordon conferences and many other talks. But it's amazing that he continues to work with me almost like a student, which is just wonderful. But he is far more competent than me in computer simulation and many other things. Now, coming back to further now with the talk, there is one thing which is an amorphous ice. Now what happened that, as I wrote in my abstract, that in the universe, in comets, in asteroids, in Jupiters of the moon, water is not as ice. It is in the form of an amorphous state. And that is one of the most mysterious substance. And that is one of the reasons so much papers in Nature, Science and many other journals are coming out to try to understand what is amorphous ice. Like recently, Jupiter's, they really studied two moons of Jupiter and found one of them they have ice, crystalline ice and some amorphous ice, other one just purely amorphous ice. So the question is that what is the amorphous ice? How does it form? What are the properties of this? It's a really very mysterious substance. And these are the other things that I'll deal with and talk today. And so one more thing that we wrote last year and it went out to review and it's kind of semi-accepted, but I don't know, I have experiences in the past when things are almost true, but then kick you out, then you go to PNAs and place like that. This is what we wrote is the multiple transfigurations. It's kind of a term, biblical term, of water on its journey towards solid state. In our laboratory there, we have done some water, anomalous bodies of water, which Biman here is there, Biman and Rakesh Singh, and I think a couple of papers were there. So many things were happening. They were working on ice. Himself published 3 papers in Nature with Cindy and other people. We are doing in our way here in Bangalore. Okay, so let me tell you what are the anomalous bodies. All of you know there is a maximum of water at 4 degrees centigrade. But there are a huge number of other anomalies. In one site in internet, they listed 102 anomalous properties. 102, and there are a huge number. One of them, which has drawn a lot of attention, is specific heat, and I probably use a little bit chalk and air to explain to you. The specific heat at constant pressure undergoes a sharp rise. This is experimented and this is a simulation, their slide. But however, at constant volume, this rise is weaker, which is only with this part is bluer. The red one is at constant pressure. This one shows much, constant volume shows much weaker. And this is the specific heat of ice. So we know specific heat of liquid is much higher than specific heat of crystalline solid, which is reflected here. Then there are one more thing that one finds when you go to really low temperature, there are some huge anomaly come, which is called liquid-liquid transition, which I will talk about a little bit more in detail. So here again, that we have up to this, the divergence like growth, that we know we can do experiment up to 230 Kelvin. Below 230 Kelvin, this water undergoes an explosive crystallization. So this is the one which is simulation. And because we cannot go below this 230 Kelvin, remember melting point is 273. So it is somewhere, here is the melting point. Yeah, here is the melting point, and then it is this sharp rise below the melting point. And because we do not know this region, there is a difficulty of doing the experiments. So let's go through this puzzle that is water, and this is an important slide. So liquid water and ambient condition below 0 degrees centigrade, if you put it in a glass or certain impurity or seed, it goes to ice, and that ice is a hexagonal ice 1H. 100 degrees centigrade, it goes to vapor. Okay. Now I lower it to 31 Kelvin. Here it undergoes an explosive crystallization to ice. I cannot do, and this is ultra pure water made into droplets. There is not a single dust particle. You lose some droplets into crystallization, those who have impurity or other fluctuations, but a number, significant number, you see up to 231. Below 231 Kelvin, which is then 42 degrees centigrade, below 42 degrees centigrade below the melting or freezing point. Then it has to undergo this. Nobody has been able to surpass this. Now reports have come that they have gone up to 227, but there is debate on that. Then, however, you can hyperquench it. You can hyperquench it and form under different conditions These amorphous ice which I talk about now, amorphous solid. It is called low density amorphous ice. These very low temperature, say you go to hypercold 50 Kelvin, then you heat it, the low density amorphous ice undergoes a glass transition at 136 Kelvin. Highly viscous liquid it forms. Then you heat it a little bit more, 150 Kelvin. Yeah, these numbers vary a little bit, but 155 Kelvin say. It undergoes explosive crystallization. So region between 230 and 150, nobody can ever has been able to see. Because crystallization no way allows that. Whatever technique we use, you can form ice in a very under high pressure condition. That is called high density amorphous ice. That itself converts into low density ice around this condition, 120 Kelvin. Then this is the cycle that obeys. So this area, which is called, which we cannot see, prohibited to us, is called no man's land. This has enormous amount of discussion. What is water, which is not too far below? You know, you have to understand, in North Dakota and Alaska, temperature routinely goes below 40 Kelvin, below 230 Kelvin. Okay. In Chicago, I have faced experience which are 26 below or 30 below. Okay. So it is not really that low in that sense, but here you never get the liquid. You only have the crystalline ice. But you know that we should be able to make here. Now, so all this transformation that I told, so then this is my normal water that goes to supercooled water up to minus 42 degrees centigrade. Then it should exist here, but we cannot explode it by any technique. We can prepare low density ice, we can prepare low density amorphous solid, high density. Then what are the natures of this? That's another condition. Since we do not know this direct information, okay. What are the other anomalies there? Okay. One is that I just told you, if I do constant volume, then it rises for some time. The constant volume doesn't show the anomaly. But the experimental conditions is the constant pressure. And this is the ambient condition, that is 1 atmospheric pressure. It has this divergent like flow. Then another beautiful property is that density not only has maximum at 4 degrees centigrade, which is not shown here because this is a little old slide. If I go to 190 Kelvin, then water density undergoes the minimum. So water density maximum at 4 degrees centigrade. You know, just bear with me a little bit, there is really very exciting and interesting physics going to come, which is as fundamental as the gate. And as I was saying that we are working on it for now 12 years. And this is the first ever talk I am giving on this problem. And I hope to give more. The reason is that it's very difficult to explain things, as you will see. Okay. If I go here a little bit more, 190 Kelvin, water has a minimum. So water has a maximum. This is of course, as I said, in a computer simulation. There is no other things we have there, but a lot of other theoretical calculations also going on. But if you take the derivative of density, that has a sharp maximum around 220 Kelvin. And 220 Kelvin is also where computer simulation gives it maximum in this specific case. 220 Kelvin or around maximum of 220 Kelvin. The region where it cannot go below 230 Kelvin, something really interesting happens. And the interesting things that are happening are the factors that are responsible for rapid crystallization of water into ice. But what is that happening has now become huge amount of discussion and controversy. What happened to water near 230 Kelvin or just below 230 Kelvin? It's almost international collaboration, war going on from every place, you know, whether it is Grenoble, whether it is Spain, whether it is Italy, people are working on this problem now. And I hope to go tell a little bit about that now. Okay, there is nothing, I'm not trying to be mysterious, but I'm trying to develop the problem. Let me now say what happened if I want the temperature. There is a property of water that's called tetrahedrality. tetrahedrally means that, water is locally tetrahedral. So water, say, this is the tetrahedrality of water. So this is the one oxygen. So these are the oxygen positions. Now I can measure the tetrahedral angle, then how tetrahedral a given water molecule is. Then I can see, okay, how tetrahedral this water molecule is. So then I can do an average. That tetrahedral water, as you lower the temperature, it becomes more and more tetrahedral. As you see, it becomes more and more tetrahedral, and this is a parameter. Order parameter, I don't want to go into it except in ice in one. A perfect ice, very low temperature, has the order parameter tetrahedrality, which is perfectly tetrahedral. One means it is perfectly tetrahedral. Now as I lower the temperature, it becomes more and more tetrahedral. More so, rate is constant pressure. More so at constant pressure. I can draw a volume which is called Bangalore polyhedra, which is a very useful construct coming from solid state geometry. That what I do around this, I can go to the nearest level, split it in the middle, draw a bisector, then I can do another like that and a bisector here, I can do bisector here, I can do bisector, then I form a polygon. That volume of that polygon, this is called Bangalore polyhedra. You might know it because it's a very beautiful geometrical concept. The volume of polyhedra gives a unique measure of volume of each molecule, each water molecule, and this is kind of form a closed package structure. Nothing is empty, everything filled up. So I get a measure of the volume of each water molecule, and that's self-exclusive. So as I lower the temperature, this volume increases. Very interesting. Everywhere in the world, you lower the temperature, volume decreases. But in case of water, volume increases. Okay. And there is a unique measure you go of the volume.